So hello guys, welcome to our new video of try data structure. And in my previous video I had explained about the try data structure and its advanced stages of try data structure, advanced trees, the compressed version. So first we go to the try data structure. So as you already know, in my previous video I explained about, but I still gonna do some basic understanding of try data structure as well. This is our try node, which is a public class, and then we have try node children, which is 26, which is fixed, and then we have a point, we have a check flag, which is bool, and then we have a node, which is we try node. The constructor we implement by default is end is false, and then for loop, which put every children is null ptr. Okay, and then we have a root node, which is only one, and then after we just make a new try node and then insert. So how does insert works? If we have a word called cat, first C will insert, or we're gonna take the example this one. If we have a, let's suppose we are inserting a and d. So you see, first we take a character of the word because it passes the word and, right, a and t, and then first it will take a word a, then it will take an index value of the character like a. What is the index value? It's smaller case, so it might be 97. Yes, so it will take 97 minus 97, which is index 0. So it will go to node children index, which is right now node is pointing to root node, which is null ptr right now. So what it's gonna do is make a new node here. So a will be, it will make a new node, this one. Okay, so this will create a new node here in this line. Okay, and then what it's gonna do, it's gonna do is node is equal to node children index. Okay, and then now our new node is pointing over here, not here. So next time when we gonna insert n, it go start from here and then take a value of c, which is 97 minus a. So the c value is 98, 99, which gonna be index 2. So the index 2 is c, so it will, the index 2 of n, sorry, my bad. So the n will be the value of whatever ASCII value of n is, and then it will take minus a, whatever the value, it will make a new node here, and then it's not a end of the string, so it still continue. And then after d, it's gonna make the same procedure, and at the end of, once we finish this for loop, it's marked as true. That makes this string is valid. Okay, same like for search, and then same with the starts with. So search is quite easy. You don't insert any new thing, you just find and return false, and at the end, return the value of it's true or false. Okay, so if we go there and then we run this file, which is result, and you will see such are true, such are 0, starts with 2 1, and starts with 2 1. So this is whatever is in the main loop. So insert r as dot, and we search for ac, which is false, and then do, and then da. Okay, so now this is the Patricia, the compressed version of try data structure. Okay, so it's quite, quite difficult to implement, but still most of the cases people do. So this is the same Patricia node. It has one label and then same flag, which is a compressed tree. And then we use vector instead of pointers. In the previous we use nodes Here we use vectors for children's because we cannot fix 26 children's here. And then we are making Patricia node string label is false right now, like empty, and then label is false. And this is our root node, same like the Patricia. But here what we're gonna do is we don't need anything like this. Okay, so we just don't need this anymore. It will be in order, so you cannot delete in the without the order. Okay, now it's free. Okay, so as you see, we have common prefix length helper. In common prefix, it's a function which you know the the types are constant string a, constant string b, and then we have a while loop which runs till minus length of size, and then b is less than length, and if a length and b length is equal to, then we return. Okay, so then we have our Patricia node here. So the how the insert works different from the normal try data structure. Okay, so we have a while loop. First we have found like false because we don't have a children. So now for this case, if we have a, okay, so first we you can see insert we have end. Okay, so what it's gonna do is it's gonna run a for loop into auto child, which will in the node children. Okay, which is right now is empty, and then match common prefixes. Okay, and then if match is 0, continue, return false. So the full match go deeper. We have two cases. One is match children label is equal to is children label dot size, and then we found the substring. So if we go further, you will see we have second case which is partial match split mode, and then we have replace child with split. Okay, so it has like four cases for only insert. So what it gonna do is, you see in this example we have a and d. Okay, so instead of you see the this part of tree will be the same. Okay, for even though compressed version as well, but for this part it will do a different thing. What it gonna do is, because a doesn't use further here, right? It has two different things. So what it gonna do is it's gonna make a new node here which is d, and then instead of a it will store a and d together. Okay, so it doesn't store ad separately, and here it store o like normal, because we don't have any further node here. So it's basically compressing the trie data structure, which is d, and then a and d, because we don't have further value from a right now. So it's gonna store like this. If we have any further value in a, then it will do some other stuff. Okay, so that's the only thing it will be changes in this tree. So instead of this, right, it will store like this, a t. So the tree is quite you know compressed. That's all, and the remaining thing are same. So this thing will go, and then the trie data structure will look like this. So the implementation is quite difficult, but these are the cases though. And then we have search. Sorry. So the search is quite similar with the standard trie data structure, but we have only one child, but here we have a vector. which can be a full word or whatever. So we have to do this thing. So it will check common prefix. If matches is equal to child label dot size, the child label is like size is basically the string size. So if the child label is equal to size, that's mean we found the substring, and we return the substring is true and break. If not, then we return false. Okay, and same like with the starts with. So here, if we run this code really quick, we run this. We have to do G++, and then we do Patricia cpp, and then we make a name which is um, result pt output pt. Okay, so it will make a executable file pt, and then we run the pt. Okay, so it says search r1, search r0, and then what it says, let me show you. Okay, so we have word inserted r as dot. Okay, so in normal tree, if you let me open up paint for you, it doesn't allow me to open. Okay, that's fine. So you can see now. Okay, so if you see, we have in normal case we have root node. Okay, and then we have, if you want to insert r, we have a here, and then we have r here, and then we have e here. Okay, and then we have s here, we mark this true, and then we have d, and then o, and then we have t. Okay, and then this mark is true. So this shows we have normal. But for Patricia, you will see we are not storing like this. Okay, so what we're gonna do is, we have root node, we insert a, we insert a, and then we insert r, and then we insert e. Okay, and then you see we have is like the s. So instead of re, we don't have further in there, we can combine like re together. Okay, it like this. Instead of using another letter e, we use combine re. So if you wanna, if you search for r, you will find the substring as well. You can find the substring, which is a re, and then combine are. Okay, so once you search for r, it will return true. If we search for ase, it's return true. If we search for du, return true. So this is how we implement the Patricia tree. I hope you guys understand. And if you want further videos about Trie Data structure, just comment below, and like, share, and subscribe my YouTube channel. Thanks for watching videos, please.